Hi, welcome to the webinar. Our speaker today is Dr. Ben Miller. He joined Gatan in 2016 from Peter Crozier's group at ASU. Ben has a background both in catalysis research and in-situ TEM. Ben's responsibilities at Gatan include proposing and then testing new products during development, demonstrating and training customers on Gatan products, and developing new and better workflows for in-situ microscopy. In his role, Ben routinely helps customers to get the most out of the data they collect. And in the webinar today, Ben will share from his experience to describe the in-situ player within GMS to work with large in-situ datasets, give a live demonstration using two different datasets, and then conclude with examples of using Python scripting to augment the built-in tools. As I hand it over to Ben, I hope that you will find the webinar useful. We look forward to hearing your comments and questions. Ben?
Yeah, thanks, Stephen. Yeah, please feel free to ask questions during the webinar, and we'll try to get as many of those answered as we can today. So I'm really excited to present about this topic today, about in-situ video and how to process in-situ data in GMS. And first, I want to just start with a brief introduction to in-situ video and what this means in the context of in-situ TEM. So in-situ TEM really means observing the sample while applying some stimulus to the sample. And so you can see here on the left of my screen a figure that I produced in my PhD to illustrate this concept of in-situ TEM. And probably I would expect many or all of you who are listening into this webinar are quite familiar with in-situ TEM. But within Gatan, what we mean by an in-situ or IS product at Gatan is one of our products that enables time-resolved data to be acquired. Whether an in-situ stimulus is being applied or not. And often this is time-resolved imaging to produce videos, and that's going to be what I talk about mostly today. But we're also starting to develop products like the Continuum IS that you see here, which can do not only time-resolved video, but also time-resolved spectroscopy. So that's what in-situ means at Gatan, but why do in-situ experiments? Why is this a really valuable thing for us to focus on and for you to focus on as a researcher? So I really like this video taken at the Fritz Haber Institute several years ago now, back in 2016. Where up at the top right corner of the screen, you can see this particle that's undergoing really very dramatic change in the microscope. This is in a gas environment at high temperature. And there's really very dramatic dynamics that are occurring in part of the sample here. And the thing that I like to point out from this video, besides the beautiful video that it is the importance of doing these sorts of in-situ experiments. Because if you looked at this sample before you applied this stimulus and then after, you might see something like this. And there might be a change in the sample after the in-situ stimulus. And so you could go through a great deal of detailed analysis and looking at faceting and morphology and size of these particles. And I guarantee if you had not done an in-situ experiment, you would never, ever guess that this is actually what happened during the in-situ stimulus. So really recording this type of data over time is extremely valuable, and recording the data during the stimulus is really important. So in situ experiments are essential for that. So in the next part of my talk, I want to go to our software, Gatan software, and what we enable you to do to process in situ data. And the first thing I want to talk about is processing data to reduce the data size and at the same time the noise. So modern in situ cameras can produce huge volumes of data. So just as an example, the K3IS, Gatan's latest camera, can produce up to 150 frames per second at the full resolution of the camera. And even with a 1 byte integer data type that's designed to minimize the amount of data, 1 frame is still 23 megabytes, and a minute of video is 200 gigabytes. So this becomes very large quite quickly. And it's possible that you might want all of this data if it all contains useful information. But to be honest, most likely it doesn't. Most likely there's some subset of the data that contains the useful information, and much of this data is probably noise and useless data that's not relevant to what you want to learn about the material. And so we need tools to be able to reduce the data size either during capture or after capture. And I'll talk in a minute a bit more about why I think reducing the data size after capture is ideal. So in GMS or DigitalMicrograph, we have the IS player, and this has been a free part of DigitalMicrograph for some time now, and it works with K2 IS, K3 IS, OneView IS, and Rio IS, and now also with the Continuum IS, which I guess I don't have here on this slide. But recently we updated the user interface. So if you have been using the in-situ player in the past, this looks very different. And we've done a lot of work on it to make the framework of the in-situ player more intuitive. We've added a few features, and we're continuing to work on more processing features that we'll be adding. And so because we're not quite done yet with this, we welcome your feedback. If you use the IS player and there's something that you think should be added, something that's really fundamental and could be applicable over a large range of applications and experiments, then please let us know what types of processing you'd like added to the IS player. But for now, I'll talk about the features that we do have. So one of the primary functions of the player, of course, is visualization, playing back data sets. And this player is really optimized for large data sets. So even if your data set is hundreds of gigabytes, it's very easy to play this back with the IS player. And the data sets open quite quickly and play back. And you'll see that, I think, in the live demo that I'm going to do in a few minutes. We also, with the visualization, we have live processing. So all of the processing that can be applied in this in-situ editor can be visualized live as you play back the data. We also, in the IS player, enable you to reduce the data size on several different dimensions. So we can reduce the data in the spatial dimensions by cropping to reduce the extent of the data, or reducing the resolution by binning. We can also reduce the data in time, so either cropping the duration of the video, or decreasing the resolution, the time resolution of the data by combining frames. And then in addition to reducing the data size, we can also we can perform drift correction. And I forgot I was supposed to be clicking. I'm sorry. We can also do drift correction with optional filtering, and I'll explain a bit more about that during the live demo in a few minutes. We can drift correct the entire image, or we can track single features like particles or grains in a material. Then we also have a new capability in the IS player now to do spatial filtering. Again, I'll show this in the live demonstration, but we can do bandpass filtering, we can do edge detection filters like Laplace or Sobel filters, and several others as well. And finally, we can export the data. So we can export the video as a video file, like an MP4. So you can put that in a PowerPoint, or we can export the data as an in-situ data set, so that you're not losing any information, and can continue to process that. Maybe you do an initial processing on the computer at the microscope, but then you take away the reduced data set as an IS data set to work on at home. And then we can also now export as an image series. This is something that previously was not possible, but now we can export as a series of DM files, or even a series of TIFFs. So I want to show an example here, just illustrative example of how much we can reduce the data size on one of these data sets. So let's say we have one of these data sets from the K through IS that's 200 gigabytes of data, and I want to process that with the IS player. I could crop to a small area around one particle, so maybe only 1K by 1K, and that actually saves me a huge amount of data that reduces the data size considerably. I could also, maybe I acquired my data at too high a magnification, and binning by 2 isn't going to eliminate any of the real data in my sample. So maybe I'll bin by 2, or maybe only 20 seconds of the 1-minute video is really interesting. That's where all the dynamics happen, is in only 20 seconds of video. So maybe I'd crop that bit of time. Or maybe I find out that 150 frames per second is really not needed, and I'm not seeing useful information in that 150 frames per second, and so I decide to sum every 5 frames. So with all these together, the data size is decreased significantly. So, and the IS player, incidentally, it also, when I bin, it automatically increases the bit depth, because I'm likely to saturate the data type. So it increases slightly, but even so, my data size is reduced from 200 gigabytes to only 0.29 gigabytes. And so you can see quite clearly, I think, how easily you could now transfer this to your laptop and work on this in more detail. So that's just an example, but what I really want to point out here is that reducing data after acquisition enables strategic data reduction. So what do I mean by that? Most likely, you would not reduce the data size in all four of these methods at once. It's possible, but most likely there would be one or two of these methods of reducing the data size, which would be most useful or least harmful to your data. So maybe it turns out you need the full spatial resolution, and so binning by 2 would actually destroy some of the information in your image. So binning by 2 would be a terrible thing to do. But since I have the entire data set already, I can try that out. I can see what happens if I bin by 2. Do I still see what I need to see in my data? If so, great. And if not, if that's a problem, then I can just decide, never mind, I'll not bin by 2. And so I can really strategically, based on the exact data set, this video, I can decide exactly how to strategically reduce the amount of data. And to do this based on the useful information in my data, not reduce the amount of data because of some limitation in the hardware or the processor. In addition to reducing the data size, a lot of these operations, specifically operations that reduce the resolution, typically also increase the signal to noise, certainly on a pixel by pixel basis. So binning and combining frames will increase the signal to noise as well. And so if we consider, just for simplicity, a signal with only Poisson noise, a perfect camera, then the signal to noise ratio is the square root of the number of electrons. And so if, for example, my signal per pixel per frame is only 4 electrons, in that case, my signal to noise would only be 2. And this is really quite a bad signal to noise. So I would like to see at least 5 to really get any information out of single pixels. And so the signal to noise of 2 is really too low if I want to look at high resolution, high spatial frequency information. But if I bin by 2 and average over 5 frames, now the mean signal is 80 electrons per pixel per frame. And so now the signal to noise for each pixel is about 9. So my signal to noise is increased from 2 to 9 by binning and averaging over 5 frames. And so this can be a great way not only to increase or decrease the amount of data, but also increase the signal to noise. And again, doing this after acquisition enables strategic noise reduction. So I can do binning if that's the thing that makes the most sense, or if averaging frames makes the most sense, I can do that. And I can tailor the exact amount of binning and number of frames that I average to the data set that I have. And I can try it and see how it works. And then if I don't like it, I can try again. You can't do that so easily during an in-situ acquisition. So the next thing I want to talk about is drift correction of challenging data. So drift correction can be performed after the data is acquired if the object stays within the field of view. That's an obvious one. And if objects are not badly blurred within a single frame. And the good news about these two requirements is that modern cameras really enable both of these. Modern cameras tend to be faster and larger. So since they're larger, the object is more likely to stay within the field of view. And because they're faster, they're less likely to be blurred within a single frame, since the frame is very short. And for example, here again, the K3IS capturing 150 frames per second at such a large resolution, this makes it really ideal for doing drift correction after the fact. But at the same time, these benefits for doing drift correction after the data is acquired are also limitations for doing drift correction live. So the live view may only display a small fraction of the data, right? As far as I know, there does not exist a monitor that can display 5,000 by 4,000 pixels. And so you simply can't show that. And also the frame rate as well, 150 frames per second. No monitor, I don't think, exists, certainly not a typical monitor, could even display 150 frames per second. And even if it could, that's not useful, certainly to the human operator who can't see data that quickly. And also, even to an algorithm, I think currently a PC would find it very challenging to process 150 frames per second at this high resolution. So the same qualities of the camera that make it ideal for doing drift correction after the fact actually make drift correction during acquisition less practical. And the final thing I want to say about drift correction is that it's not just aesthetic. It does tend to make your videos look nicer, but drift really distracts the viewer from real changes that are occurring in the sample. And so if you are looking for something subtle happening in your material, if the drift is fast or if the drift is inconsistent, you might miss those subtle real changes in your sample because of the drift. And also drift can make some image analyses, automated analyses, impossible or inaccurate. So the IS player has tools for drift correction. These are designed to be simple, where you can measure the drift and align the video by the entire image frame or by just a region of interest. And this uses a cross-correlation algorithm. And we can also apply filters prior to the cross-correlation. And these filters are user configurable. And we'll see more of this as I go into the live demo here. You also see a preview of the drift correction during playback. So that's a nice feature to enable you to see if your parameters are good and if it's likely to work. And then the full drift correction is performed during export of the data. And so we'll see that in the live demo. One thing I'm not going to show in the live demo today are the stack tools for drift correction. So I mentioned in the previous slide that the tools in the IS player are at the moment designed to be simple. Yeah, just simple. Powerful, but simple. The stack tools for drift correction in GMS are designed to be flexible and powerful. And in the stack tools for measuring drift, drift is measured first, and the result is displayed actually during the measurement in a line plot. So this sort of plot updates live as you measure the drift. And then based on the plot, you can choose whether you want to apply that or not. And as you can see, there's a lot of options, which I'm not going to explain at all here. But just I put them here to show that this is really a flexible tool. And if you want to use this on an in-situ video data set that you have, please contact us, contact me, and I can send you a script that can convert the in-situ dataset to something that can be used with this more flexible but complicated drift correction tool. Okay, so now I want to switch to the live demonstration. So I have 3 different samples that I'm going to show during this demo. The first, or I should say 3 different data sets. So the first is a tin nanoparticle sample that melts and crystallizes, and that's in selected area electron diffraction. And then the same exact sample, but in dark field TEM. And then finally a zeolite sample that's undergoing beam damage, where that was captured in counted mode with the K3 IS. So let me switch screens here. Okay, so this is GMS. I should mention that I'm remotely accessing a system in California. I don't have these massive data sets at home. So I log in remotely and access this system. Hopefully that doesn't degrade your viewing experience as we go through this. But it was working pretty well for me yesterday. So I have this data set. This is the raw data. This is 50 gigabytes of data in this data set, 25 frames per second. And if I play back through this data, I can see, there are dynamic things happening. I can actually speed this up quite a bit and play through all 50 gigabytes quite quickly here. And okay, so there we go. We're playing through 50 gigabytes of data very fast. I can also actually do processing on the fly as I'm doing this. So I can combine frames together. So let me turn this on. We'll combine 10 frames, average over 10 frames. And you can see now I don't know how well you can see that. The signal to noise is a bit better than it was before. And we can turn that on and off live. So that's nice. So that's binning and combining the frame. Oh no, I didn't bin yet. Let me do that as well. Okay, so there we go. Now we're binning, and all of this I'm doing while playing back the data. Maybe I'll turn on the auto survey there. Yeah, another thing actually that I want to point out here is the contrast limits. So all of these, while I'm playing back my data, this is real data. This is not just a display or a screen capture. This is real, what I would call real data. So if I look at the central spot, for example, it kind of looks. Let me pause this. Let's go here. And it looks in this view of the data, this display of the data, like all of this is saturated, but it's actually not. And if I was just doing a screen capture of this data, I would lose everything in this spot. This would all just be white. But if I have real data and I go in here and I change my contrast limits significantly, now I can see actually there is a very tiny spot that is saturated. I know it's saturated because I've looked at this before, but it's quite small. And if I go back to auto survey, all of this out here looks saturated, but it's not. And the same goes for these spots out here. It looks like maybe these are saturated, they're not. And because I have real data and not just a display of the data, not just like a screen capture, then I can adjust my display parameters and really see a large amount of detail here, and see all of the full get the full value out of my in situ data. Then one last thing I want to show on this data set, you may have already noticed as I play back here, there is a little cursor that is moving in this temperature plot. So this temperature plot is actually 3 plots: temperature, the temperature set point, and the power being applied. This is in a DEN solutions holder. And we can do this because we were actually controlling the DEN solutions heating holder in our software in GMS. And so with holders that we control, we were able to correlate the temperature and produce a nice plot like this. And not only does this play back as I'm playing the data, but it's also interactive as well. And so I can click anywhere in this temperature plot and it shows me the data. So if I'm looking at these low temperature regions here, then I see a crystalline sample. And if I switch to these high temperature regions, I'm going to see that's where my sample is amorphous. It's melted. So that's a nice little feature that's available if your holder is being controlled through GMS. And if you have a Hummingbird or a Protochips holder, those can't be controlled through GMS. So talk to Protochips or Hummingbird and ask them about integrating those into our software if that's something you're interested in. Okay, so I think that's all that I want to do here, all that I have time for. Yes, time is slipping by. Okay, there's so much more I could say and do, but we'll move on here. So this is the same sample, the same experiment. I guess maybe you can see down here this very similar temperature plot. And so again, I'm melting and crystallizing this tin nanoparticle sample, but this time looking at it in dark field, classic traditional dark field TEM. And I should mention that both of these were actually captured with the camera at the end of the spectrometer. And yeah, that was something I forgot to mention. So like this data was actually filtered diffraction. And I even switched, but anyway, I don't have time to describe all that. Okay. So this again is the camera that's at the end of the GIF, and we're looking at dark field TEM, and I'm playing back through my data set, and maybe I'll even make that a little bit faster. So we can see that there's some small drift every time that I cycle the temperature. It drifts slightly. And it's quite good. It's quite a small drift, but still noticeable for sure. And so something I would like to do is to drift correct this sample. And so again, I think the first thing I'm going to do is to combine frames to increase the signal to noise a bit. And so, oops. So we can do that here. And so now we can see a bit better signal to noise. Let me go back to not combined. So my data is good, but certainly summing several frames together increases the signal to noise here. Okay, so that's good, but I would really like to drift correct this. And so what I want to do is to use this align or drift correct checkbox, and I want to do the entire frame. And let's start with no filter, and I'll play this back. So now it's actually doing this drift correction live. And so maybe you can see that. Okay, so there's an example of very poor drift correction. It's messed it up completely, and I have no filter used, so I'm not very surprised. But that's fine. I'll restart it here. So, but I'm doing this drift correction live during playback, and that's what I really want to point out here at the moment. But it's not perfect. It's maybe not even good. So I want to filter my data first before doing this drift correction. So I can select a filter here, and so I'm going to select this one. But how do I know what filter to use, or how do I determine what type of filter to use for this particular data set? Because it might be different for a different data set. It might be different for bright field TEM. So the way I do this is with this image filtering palette here. And so I can go up here and I can select the same filter. Okay. And I can click this live button. And so now I can see my original data and the filtered data. And I can see what effect these parameters of my filter have on my data. So I can adjust all the parameters in real time, and yeah, see exactly what effect that has on my data. But that's still not really what I want. What I really want is to see what effect these filters are going to have on my drift correction. So for that, I'm going to use this live to button. But first I need two images. So I'm going to find a place here at the start. I'll copy and paste. And to paste that, just as a tip, a GMS tip, I'm using Control-Alt-V. Oops, I should turn off that. So Control-C to copy, and then Control-Alt-V to paste. Okay, so now I have two images from this data set at two different times, and I'm going to click this Live To button. So I can select the two images, those are the two I want. And so now I can see the original image 1, original image 2, filtered image 1, and filtered image 2, and the cross correlation between those two filtered images. And so I can go in and look at this cross correlation, and what I want to see is a single very bright peak that will be easily found and always be the maximum in this cross correlation. So maybe this is not really what I want, and maybe I need to go in and change my band pass parameters or this low pass parameter. And I can go in and tailor this filter very specifically to my data set. So I'm for the sake of time, I'm not going to do that in detail right now. I already put together the filter and adjusted it just the way I wanted. And yeah, I wish I had 2 hours and could show you all of this in detail, but anyway, maybe another time. So, but this filter that I've now configured and been able to set up very precisely for this exact data set, I'm now going to select down here in my drift correction, and I can apply that while I'm playing back the data, and more importantly, while I'm processing the data. So let me go to the export here, and I'm going to export an in-situ data set. And let me make sure all my parameters are correct. Binning, combined frames, that looks good. Align, full frame with my filter. Okay, so I think that's all good. So now I'm going to click export, and that's fine. Okay, so we'll go with that. And so now it's going to go through and process every frame in the in-situ dataset and produce a new in-situ dataset with this processing applied. And so you can see here that it says it's going to take 5 minutes. And since we don't have 5 minutes to spare, I'm going to just cancel that. But hopefully you could see that it was actually doing the drift correction live. It was showing its progress during that export. But I already have several data sets here that are done. And so I put these together with different processing. So this one on the top right is with no drift correction. And so if maybe I zoom in on one of these, it's doing the combining the frames. So we're getting a better signal to noise, and the data set is smaller, but there's no drift correction. And then if I go to this one, I'll zoom in again and play this one. So this has drift correction applied, but I'm not using any filter. So I'm selecting here for my alignment filter, none. And you can see it's doing something, but it's not perfect. And this particle is sort of drifting to the right over the course of the video. So I'm not very happy with that. It might be okay, but here is the same data set with the filter applied. And so now we can see, again, maybe it's not perfect. I still see a slight vertical movement, but it's dramatically better. And the sample's not moving to the right over time, and certainly not moving anything like this original data, where it moves quite dramatically during the video. Okay, so that's drift correction of this rather challenging data set. Challenging because the contrast is changing so dramatically over the course of the video, especially if we look at the entire data set. That's a challenging data set to drift correct properly. Okay, so I think that's all that I want to show there. Yes, I am running short on time here. Okay, so the last data set that I want to show is a counted data set from the K through IS, and this one is taken at quite a low dose. So this is a zeolite sample that's beam sensitive. And so we wanted to image at a very low dose rate. So this is 23 electrons per angstrom squared per second, which, just to put that in context, that's about 2 orders of magnitude lower than you might typically use for just a standard high resolution image. So just 23 electrons per angstrom squared per second. And if I start to play back through this data, probably the first thing you notice is you can't see anything. That's not just you. I don't really see much of anything either. You can vaguely see an outline here. But that's fine, and the data here is good. There's just not much contrast per frame. So I'm going to use this combine frames feature, and this time I'm going to sum together 20 frames, but only skip 10. So this is sort of a running average. And if I start to play that back, now we can start to see something. I also happen to know that for this data set, we can certainly bin the data. And how do I know that? If I do a live FFT here of my data, I can see that almost all the information is right here in the center of the FFT. And that's really telling me that I'm oversampling the data here, and I could bin it and not lose any real information in my image. The microscope isn't giving me information at high spatial frequencies, so I won't lose anything by getting rid of those. So if I bin my data, and now I do a live FFT again, now I can see I still have all of these lattice spacings. Maybe that's hard for you all to see. I still have all these lattice spacings, and I haven't lost anything. But if I were to bin this by too much, let's say by 8, and now do a live FFT, now I'm losing information. Some of my lattice fringes are going outside of the FFT, and that means I'm not sampling the image enough. I've binned it by too much. But of course, as I talked about in my presentation, the great thing about doing this after the fact, not before you capture the data, is I can say, okay, well, that didn't work. That was bad for this particular sample and this particular video. So I'll just go back to a binning of 2, which I know works well. Okay, so that's that, and it's processing, it's binning by 2, and also combining 20 frames in this really quite large image that was over 4K by 5K, and it's doing this in real time. Let's see. Oh yes, the one last thing, forgot to show this. And this isn't very important or relevant to this webinar, but you can see the quantization actually in the histogram here, which is quite nice. So this is 1 electron, 2 electrons, 3 electrons, and so on. So that's kind of nice. Okay, so and because we're using an integer data format and these are small integers, it's actually important to sum the data rather than averaging the data. And so we have several options here, including sum and average. But for counted data, we definitely want to sum. So, okay, in this data set, the data the sample is drifting actually quite a lot. And we have really high spatial frequency information here. And so it's actually going to be a problem, this drift. As I sum together many frames, we're going to get blurring. And so for this data set, I'm actually going to check this box that says align before combining. And this will enable me to, this will align the frames even before they're summed together. This is quite important. One thing I will note about this is that this makes the whole processing much slower. So I don't really want to play this back. I could, it wouldn't crash the system. But even if I try to advance by just to one other frame here, it's taking quite a long time, there it is, to do all the alignments of these 20 frames that are 4K by 5K and then sum them all together. So I don't really want to have this checked while I'm playing through my data, but I can check this and use that as I export my data. So I'll do that in just a minute. And for this particular data set, I don't really need a filter for the alignment. And in many data sets, you don't. And just the simple cross correlation is good enough. Okay, so I'm going to export this as an in-situ data set with the align before combining checked and the combine frames and the binning. And so if I do that, and we'll just see how long that is going to take. Too long, I'm sure, for us to watch it to completion. But okay, so it's saving one frame. It only has 74 to do because this data set only had 740 frames originally. So only 6 minutes, not too bad, but too much for us today. So I'll cancel that. And again, like a cooking show that you watch on TV, voila, out of the proverbial oven, we have the process data set here. So now what I want to do, and actually want to reopen that. Open this one, 0.5. Okay. So now what I want to show is exporting a video. So we've exported a couple data sets as in-situ data sets, but I want to show exporting as a video as well, like an MP4. So I'm going to put an ROI because this particle is really the one that I'm interested in. All the rest of this data I don't really care about. And again, this is where I can strategically reduce the amount of data because when I was at the TEM, I didn't know which one of these particles was going to be good. But now I do. Now I can go back and choose this particle. And I can say I want to crop this region of interest. I want to, I've already combined frames, I've already been, so I don't need to do that, but I'm going to align or drift correct. And this time I'm going to align just that region of interest. And then if again, I should play this back and show that as I play back, the region of interest is actually moving. I don't know how well you can see that, but it's moving with the sample because it's tracking that sample. So it's doing that during playback, but also during export. So let me go all the way to the end and see how far my particle moved. Okay, so I think I can put my ROI about there, and it won't move off out of the field of view. And then for this data set, I'm also going to do a bandpass filter. And I am really running short on time. So I'm not going to explain this too much or show the live FFT, I think. Maybe if someone has a question, I can go back and show that. Okay, so I'll choose video and export. And I can choose the frame rate of the output. I can also add a scale bar and a timestamp. Maybe I'll name this something different. And okay, so now maybe you can see at the bottom of the screen, just barely, you can probably see the ROI again is moving over time. And the video itself is keeping that same region of the sample throughout the video processing. And this one is really quick, so we'll go ahead and let this finish and open that up and see how it looks. Okay, so that's done. Here it is. And oops. So we can maybe see that playback. It's awfully jerky on my monitor, so it's probably even worse for you all, and I apologize about that. But it's if we were not looking at this over TeamViewer, this would look quite fabulous. There it goes. Maybe that's a little bit better. But we can actually see in this video the degradation of this material over time, and it's yeah, quite a nice result, I would say, and something we could certainly put into a presentation. And so from something, let's go back to the original here, something that looked like this and didn't look like much. There was good data here, but it wasn't much to look at. We can produce a really nice video, and the original data was 16 gigabytes, and this video is only 30 megabytes. So that's quite a reduction in the size. Okay, so we'll have to end the live demo there. Yeah, wow, I am really out of time. Okay, so I think I had a whole section here on scripted data processing with Python, and unfortunately I'm gonna have to skip most of that, I think. And just say that scripting really provides infinite flexibility to do any type of processing or analysis that you want, any type of visualization. So it's really valuable. And recently, Gatan has implemented and integrated Python scripting into our software. And so this is really powerful, and I'm really excited about the possibilities of using Python in GMS. And here is just an example of a Python script that I've written and that I've put on our website. So you can download this script today and try it out, where this is processing this in-situ data set, where again I'm melting and crystallizing, this tin sample, and we can see profiles of the FFT over time and see when that melts and crystallizes and melts and crystallizes. Okay, so yes, and then we could do things with scripting like producing an FFT video from an in-situ data set, and then in video editing software, I can combine the FFT video with the real space video. And so for samples like this one, where we're seeing degradation over time and we're losing lattice fringes over time, that can be quite nice. Okay, so now I think this is the same, actually the exact same data set during acquisition. Actually, I'm doing the Python processing live during acquisition, but yeah, I don't think I have time to really describe this fully. If you're interested in Python in GMS, I just presented a webinar last month about Python in GMS, where we spent the full hour on that topic. So I'll refer you back to that. And yeah, sad I don't have time to talk about my last example at all. But you can go and look at that webinar on Python and GMS. We have a video that shows you how to get started, how to install the software with Python. And we also have this web page where there are example scripts, including the one that I showed for live processing of the FFT and processing of the FFT of an IS dataset. And then we have some additional resources for the IS player. So I'm currently working on a whole series of short tutorial videos so that you don't have to wade through an entire hour-long presentation to learn about one of these features that you have a question about. So these will be going up over the next couple of months, and I'm excited about producing those short tutorial videos. If you want to install this and you don't have this in-situ player, it is available. It is free. And so this website will show you where to get the license for this. And if you have more questions, please contact us, and we can show you how to get started with that. And we'd love to have your feedback on the IS player. So, okay, I'm already at the hour mark. Yeah, if you have any questions, please continue to submit those. And we will try to answer all your questions that you've submitted via email for sure over the next week or so.
Yep. And with that, we'll conclude. Thank you for your time and attention, and we will get back to those who have submitted questions. Thank you.